Hi everyone, my name is Patmari Sakuna, and today I'll be talking about the unimolecular diffusion. Trying to where in the end goal for this project is trying to derive the flux law using three different types of equation. And with me are Just and Jesse. Okay, so as I said earlier, I'll be using the molecular diffusion, which is the UMD, to derive the flux equation, and I'll be telling you using a diagram. My main goal is to get the flux equation by using a diagram to explain and break down the equation for you all. So going down to what I have solved so far, I will be explaining what I've done. So here I drew two different diagrams. In the diagrams you can see this is A and this is B. A is where the contact is, and B is just above the contact, and that's the stagnant air. So I'm not going to work with this whole thing right here. I'm not going to work with everything right there. What I will just be doing is to bring out everything from the red up. So which comes to the second diagram. So in this second diagram, I put it as YA, and YA is equals to 0. That means that is A is gradually diffusing into the stagnant air B.
What does the Y represent?
The Y represents the mole of A, like the mole from where the whole content is gradually condensing to B. So in this case you see it, and I gave some little notes, like in this case I put no accumulation because whatever is going in is actually coming out. So all the air that enters must exit. That's just what this yellow highlight means in this diagram. So as I said earlier, we are only focusing on the top of the container, which is this part of the container. I'm not focusing on the A. And so we are looking at A as it diffuses through B. So diffusion is just like spraying, like let me say a spray in one corner of a room, and it gradually diffuses into the other corner, into the rest of the room. So using this, we're going to use flux equation as, this unimolecular diffusion UMD is just basically using one dimensional equation to derive the main equation. So in this case, what we'll be assuming is that it's steady flow, and the steady flow transfer of A through stagnant B, according to the diagram. All right. And in this case, B is negligible solution in A, and A and B don't react. Both of them don't react, no matter what. Okay, so mathematically, we say that NAZ, and Z is just the upward direction from A to B in the diagram. Yeah, so NAZ is equals to C diffusion of AB is equals to the difference in YA over the difference in Z plus YA into NA times Z. So by reacting into a fixed law equation, this is the fixed law equation according to the textbook 18.1-2 or 18.1-22, which is either going from A to B or B to A. You can get this final equation, and this final equation is just by rearranging the fixed law. You get this final equation right here. So by doing a quick material balance, we know that whatever goes into the equation must go out, according to what I said earlier in the diagram, right? Whatever is in equation A, whatever is in solution A has to go out, right? So also the assumption is no accumulation. No accumulation is just whatever is coming out, going in from A has to go out from B. Whatever is coming in has to go out. So with that in mind, I just did the main balance equation. I just balanced everything, and I came out to the final equation, which is the flux equation. Na is equals to C dA over Z minus Z1 natural log of 1 minus YA2 over YA1. So according to the reaction right here, the going from A to B at that critical point where the line rolls, like it's diffusing from A to B, that's where it starts as Y. Sorry, excuse me. That's where it starts as YA1 and the upper part is YA2. So that's how I got this equation right here. So just this remaining part is just showing the natural log of, I'm trying to calculate the natural log of the flux equation, which you can do. And this is the final equation I got for the natural log of equation. And now we'll be passing down this to just who'll be talking about the molecular diffusion of flux equation.